So now we are talking with Dr. Adam Kowalski. Dr. Kowalski has been at CU since 2016 when he joined the National Solar Observatory and the Department of Astrophysical and Planetary Sciences as an assistant professor. His research interests lie in solar and stellar astrophysics. He's got a specialization in spectroscopy of optical and ultraviolet emissions in stellar flares. Uses state-of-the-art modeling codes combined with analysis of data from ground and space-based observatories like Hubble, IRIS, and the APO ARC 3.5 meter telescope. Uses those to understand how the lower dense stellar atmosphere is heated in response to the sudden release of magnetic energy during flares. He's also interested in developing new media for the dissemination of scientific results to the public and in establishing collaborations across disciplines. This is a whole big thing. So thank you so much, Adam, for joining us today.
Oh, thanks a lot for having me.
We are super stoked. So I figured we'd start off with maybe kind of an easy question, but people don't always realize that the sun actually has layers. The sun and most other stars too, having things like a core and an atmosphere and whatnot. So can you kind of give us a quick rundown on the structure of our sun? How is it made up?
Sure, yeah. So let's start at the center of the sun, where all the energy that we get at Earth ultimately originates. The center of the sun is called the core, and it's so hot and dense there that hydrogen nuclei slam together and fuse into helium nuclei. And this releases a lot of energy. And this is what eventually escapes the sun and reaches Earth. But it's a pretty complicated story, actually, from starting at fusion and then reaching our skin while we're on the beach getting tan. After fusion, there's energy that's released, and it keeps the core hot. In particular, radiated energy, or just light, starts making its way out of the core, and it kind of bounces around in packets of energy called photons, and it bounces around for quite a while. At some point, then, it kind of takes an elevator ride the rest of the way to the surface of the sun. And this elevator ride is through a process called convection. Basically, heat rises. So similar to how water boils in the stove, there's hot pockets of air that bubbles to the surface on our stove. There's hot pockets of plasma that bubbles to the surface of the sun, carrying this energy, which ultimately was produced in the core itself. By the time it reaches the surface, though, the material has significantly cooled off, and the core is about 15 million degrees, whereas the surface of the sun, where the energy boils to the surface, is about 6,000 degrees.
Is still this a Fahrenheit or a Celsius there, or Kelvin?
This is approximately Celsius.
Okay.
Yeah, yep. So scientists, we tend to just talk in degrees. We use kelvins, which is 270 degrees from Celsius. So I'm talking in thousands and millions. So it's essentially Celsius. By the time this energy boils to the surface, it'll eventually reach a point where light can now escape these pockets of plasma. All right, and this part of the sun is called the photosphere, and this is what we call as the visible surface of the sun. It's very bright, obviously, but surprisingly, it's not a surface at all. It's actually about 100 kilometers thick, and the plasma here, partially ionized gas here, is about 100 times less dense than the air around us. But because it's so hot and because it's made of hydrogen, it glows very brightly. From here on out, the light can then escape essentially directly to the Earth and then our eyes. And this is the visible light that, that can escape. We know, though, that this is not the end of the story for certain other types of light. So from the photosphere, the temperature then drops off from about 6,000 to about 5,000 degrees. And you'd expect then the temperature to keep dropping off, to the temperature of space, which is near absolute zero. But in fact, it doesn't. From here on, from the photosphere outward, is what we call the solar atmosphere. The density decreases, then the temperature decreases. Surprisingly, the temperature starts increasing again. This is very strange. So if you start on the the surface of the Earth, the temperature is a nice 80, 90 degrees today in Boulder, Fahrenheit. But if you go and climb a mountain, a 14er, the temperature cools off and it gets cold. You need a parka. Okay, this is what we expect to happen with the sun's atmosphere. But in fact, at some point it starts getting hotter again. It increases in temperature to about 6,000, then to 10,000 degrees. And this is what we call the chromosphere. And it actually shines very brightly in red light. Then suddenly, about 2,000 kilometers above where the energy initially boiled to the surface, the temperature suddenly jumps to 1,000,000 degrees. And this has been a long-standing mystery why this happens. And we think that it's due to the fact that the sun is actually a magnetic monster. There are magnetic fields sticking out everywhere in the surface of the sun. And in certain regions, the magnetic fields are stronger and they're tangled and they can store and release energy, causing certain regions of the solar atmosphere to be hotter than what we expect, as hot as millions of degrees. And this outer, what we call a layer, it's a very large region outside the solar surface, is called the corona. And it shines brightly in X-rays. So that's in general the story of the sun from the core to the corona.
Perfect. That's great. That's a nice brief summary. So really quick, there are a couple of questions that I had as you were speaking. First of all, I love the term magnetic monster. That's great, and that is what I will refer to the sun as from now on. You mentioned all of these temperatures that we starting at the core, moving outward. It's really hot, and then we kind of cool down towards the photosphere, right, which is what we might think of as the surface. Then it gets hotter again as you continue outwards into the atmosphere of the sun. How do we know the temperature of these parts of the sun? Because I assume we're not there with a thermometer in our hand, right? Taking the temperature of the sun, we'd be ash. We'd be worse than that. So right. How do we tell?
Yeah, that's a really good point. So let's start at the core. How do we know that that we're so confident in our theory of fusion and that the core is 15 million degrees and it's very dense? In addition to helium nuclei that's produced in fusion, there are byproducts in this process. And one of these byproducts are neutrinos. And neutrinos interact very weakly once they're produced. So once they're produced in the core, they fly directly to us without interacting with anything, without bouncing around, without getting absorbed.
That's what photons do. Photons can't just come straight out.
Right, exactly. Photons cannot just come out. They interact with matter.
Okay.
With nuclei, with electrons. It really is hard for them to get out. But neutrinos just zip right out. And we have some very sensitive detectors on Earth. And we can measure the amount of neutrinos coming from the core. And this is how we can ultimately tell the temperature of the core and the conditions in the core. Now in the solar atmosphere, we use spectroscopy. So we measure the amount of light as a function of its color. It's specifically, going from Roy G. Biv and the optical, but we can also measure the wavelength or energy of light outside the optical band, for example, in ultraviolet or X-rays. So we can measure the amount of X-rays, the amount of ultraviolet, in certain parts of different regions of the solar atmosphere, and that gives us the temperature.
Got it. Thank you. So that's just a brief aside because I've had plenty of people ask me, like during shows at Fiske, they're very skeptical about how can you know so much about something that's so far away. You claim to know these things with kind of crazy certainty, and I'm like, well, so that's a
Right.
perfect answer for us. Thank you, Adam.
Sure.
So I kind of will move in the direction kind of your research and kick things off with the question of what is a solar flare?
Sure. So a solar flare, in a few words, is just a burst of light from the solar atmosphere.
Great. That takes
Now
care of
that's
that.
that's all it is. The light comes in various forms. It comes in optical, at optical wavelengths. It comes in X-rays, radio waves are produced in during a solar flare, ultraviolet. So it's really it's a burst of light across the entire electromagnetic spectrum.
Crazy.
And in particular, you look at these solar flares in optical and UV mostly. So what kind of different things do you learn looking at them with these two different wavelength regimes?
Right. So actually, it comes back to the previous question. We learn about the temperature. So by measuring the amount of UV light compared to the amount of optical light, we can get a temperature of the flare. And what we typically see is very dense regions of the atmosphere become very hot, about 10,000 degrees. So you go from about 6,000 degrees to about 10,000 degrees by through measuring the amount of UV to optical light. And we also get the density. We find that this is very dense. And when we run computer models, it's very hard to increase this amount of material, this density of material, to 10,000 degrees from 6,000 degrees.
Really quick, I guess, so what's the maximum temperature that we see in the atmosphere of the sun? What's the hottest we've seen it?
So in a flare, the corona goes from about 1 million degrees to tens of millions of degrees, 30 million, 50 million degrees in the sun.
Wow.
On other stars with much more energetic flares, the record holder is a relatively nearby M dwarf. Its corona went from 6 million degrees to 300 million degrees.
Wow.
So hundreds of millions of degrees is possible.
And remind us again what the temperature of the core of our star is.
15 million.
So would that imply that then temperatures would be great enough in the atmosphere to start nuclear fusion?
People have actually considered that. The missing ingredient here is density. In the core, it's 15 million degrees, very hot, but also extremely dense.
Sure.
So 160 times denser than water. The corona is 10 trillion times less dense than water.
Okay.
In a flare, even it's maybe 1 trillion times.
Right.
So less dense.
Got it. Cool. Okay, so you know, in doing presentations at the planetarium, and I'm sure you've encountered this as a solar physicist yourself and giving talks and such, it seems like people are increasingly worried about solar flares and how they could affect us here on Earth. What sorts of flares might we need to worry about, if there are any, and what's the real risk of one hitting us?
So I don't want to cause alarm and overplay the danger from flares, but I also don't want to underplay the risk here. So we as a society are taking a lot of measures to prepare, and for various government agencies, satellite companies, energy companies, must all communicate with each other, in addition to those who observe the sun to try to predict when flares happen. And they all are communicating with each other, kind of behind the scenes, right? So, you know, the risk is certainly known to the powers that be, and the energy companies are ready to, stop a catastrophic failure across, the country here. The trick is predicting the flares. Predicting flares, especially a large flare, is kind of like predicting a tornado on Earth. We know when the conditions are right for a tornado, right? We just don't know if it's going to happen, and when exactly it could happen, right? So we have a large fleet of satellites looking at the sun, studying the sun, taking immaculate images of its magnetic fields, determining when they're twisted and entangled enough such that we might expect a large flare. And we get, these data come down essentially in real time to us. So we know when the conditions are right for a large flare to happen. We just don't know if and when it will. Right now, we don't have to be worried at all. There's a very, very low chance of an event happening right now because we're in a time called solar minimum, where there's not much strong concentrations of magnetic field in the sun. There aren't many sunspots. In a few years, there will be many more sunspots and many more flares. The thing about flares is that like small flares happen very frequently and very extreme flares happen very rarely. This is a well-known property, okay? So just because a flare went off doesn't mean we should worry about it. The other aspect about it, about flares and the danger to us is there's more than just the flare that occurs. What essentially happens is you have some magnetic fields which pop up through the surface of the sun and they get all tangled and twisted. They get stretched, kind of like a rubber band gets stretched.
So can we think of these magnetic fields as like strings that can interact with each other almost like
you absolutely can. Yeah, that's a good analogy that we use. Of course, magnetic fields are extremely complicated, and they interact in ways that are not normal in our day-to-day life. For example, they can interact with each other and reconnect into a different configuration. It's a very strange process, and this process is a matter of intense study across many disciplines. It occurs in our magnetic field, the Earth's magnetic field, which ultimately leads to the aurora. It occurs in magnetic fields across the universe. And the sun is one type of environment where we can study this remotely. And this is what ultimately actually causes the flare, is this stretching of magnetic fields. They essentially snap and reconnect. And when you stretch a rubber band, right, and then it breaks, it will snap and then hurt your finger, right? It has released the tension in the rubber band has gone into kinetic energy and hurt your finger, right? That's what happens in the surface of the sun. So the magnetic fields stretch, they snap, and they retract towards the surface, causing the atmosphere to heat up, causing the corona to heat up to tens of millions of degrees, causing the lower dense atmosphere to heat up to 10,000 degrees, producing the optical and ultraviolet light. And this energy conversion process is a very complicated process, and we're still trying to understand exactly how this happens. So the magnetic field has basically reorganized itself into a lower energy state here, and it put all its tension and anger and stress essentially into the atmosphere. That causes the flare. Okay, now I said that the rubber band broke, right? The magnetic field broke. Okay, similarly, there's pieces of the magnetic field that break off from the sun entirely and like a slingshot fly off from the sun. Okay, this
so
carries
a piece of magnetic field is moving away from the sun.
Exactly. Yes. And it's carrying mass from the sun, from the corona, out. And this is what we really need to worry about in terms of space weather.
Okay.
Whereas light travels, fast towards Earth, the flare light, the X-rays can ionize our upper atmosphere and cause a disruption in radio communications. The matter and the mass in the magnetic field actually takes a day or so to reach Earth if
Okay.
it's directed at us.
Sure.
So this, what we call a coronal mass ejection, is another part of the flare process that we need to be concerned about, especially for the large flares and especially if it's directed at us. We had a close call in 2012 when there were a lot of sunspots and flares happening in 2012. The coronal mass ejection missed us though. There were some studies here done at LASP on the potential impacts of this event. The point is, it's a complicated process. We have warning from the flare itself, about a day's warning to prepare for this coronal mass ejection if it's happening, or if it actually occurs. Not all flares have a coronal mass ejection that occur with it.
Sure.
And if it's directed at us. We do have some, time to prepare for these things, to get ready if it does seem like it could be dangerous.
Without being, too scary, like you said, what would be the consequence? What would we expect to happen if a coronal mass ejection were directly on track for the planet?
So we are safe on Earth. We will not get any additional radiation exposure or anything.
Nice.
Thanks to our thick atmosphere, thanks to our very strong magnetic field of the Earth, the coronal mass ejection slams into the Earth's atmosphere and its magnetic field. So we're really protected down here.
Very cool.
It's really the fact that since our magnetic field takes the brunt of the force, it bends itself and it reacts. This will cause currents to flow through the ground of the Earth.
Electrical currents?
Yeah. So actually, currents can flow through the ground of the Earth, and as a result, there can be surges in the power system. This is really the main concern: is that the power, centers will be overwhelmed and cause blackouts. That's the main concern here. In addition, a lot of our radio communications occurs at low frequencies. We actually can communicate with places on the other side of the Earth by bouncing radio waves off the top of our atmosphere. And the X-rays from the flare can ionize this and disrupt our communications. So we can, in the 1960s, there was a false alarm. The United States government thought that our radio communications were being jammed. So we loaded up our fighter jets, but it was really just a giant flare that interrupted our broadcast to our bases across the world.
That's super cool.
In addition, you might want to take, for flights that go over the pole, for example, if you're, flying to Asia or something like that, because of the disruption in our magnetic field, there can be particles, electrons, protons that are funneled towards the poles, and parts of the coronal mass ejection cause this. And so flights that go over the poles have to be redirected. That's another important aspect.
I imagine there's some consequences for things like satellites too, that are
absolutely
far up and outside of our atmosphere.
Yeah, so the list goes on and on here. Satellites are at risk. For a variety of reasons. One, they can be directly hit by the radiation from the flare and from the coronal mass ejection. We want to have significant warning so that we can put them into a low power mode, so we can prevent significant damage. Also, I said our atmosphere actually takes a bit of the hit. The X-rays from the flare can cause the upper atmosphere to heat up, and when things heat, they tend to puff out. And so the satellites will have increased drag in the very tenuous outer regions of our atmosphere due to this. This can cause, the satellite to completely plummet to the Earth, which has happened before, or it can just kind of decrease the lifetime of the satellite because it gets basically dragged to a lower orbit, and there's not much we can do about that.
Just from a kind of a logistical standpoint, I guess, do we see on the sun, do these flares happen with equal chances kind of in all areas, or are they kind of concentrated around the solar equator, or are they more likely to come directly at us more so than kind of grazing glances or whatever?
Yeah, so so I mentioned that the sun goes through cycles every 11 years. We have a time period of about 3 or 4 years where there's lots of flares. And there's lots of flares because there's lots of sunspots. This is where magnetic field comes to the surface in especially dense concentrations. So if you have one sunspot formed and then another sunspot formed next to it, magnetic fields can get tangled. Okay, there's just not room for these magnetic fields to spread out. All right, they get tangled. They're colliding and getting twisted and stretched and producing the flares. That's when you have these interacting sunspots. For some reason, sunspots emerge at a particular latitude, about 23 degrees north and then 23 degrees south. All right, and this is kind of an open mystery for the sun. And this is where flares tend to happen. Now, the flare light goes through space in all directions. So as long as it happens on the side of the sun facing Earth, we can be impacted by the flare. But for the coronal mass ejection, really there's a particular location where we're most susceptible to it. Uh, and so because it travels directly out from where it's produced.
So, Adam, you are studying flares on M-dwarf stars, which are much smaller than the sun, but have huge flares. What is it about these tiny stars that makes them so prone to giant flares?
Oh yeah, great question. This is a matter of intense research, actually. We think we have some idea of several of the ingredients that go into making these tiny stars such prolific flare stars. For one, some of these what we call M dwarfs or red dwarfs. They're about a third the size of the sun, a third the mass of the sun. They're red. Their photospheres are red. Our sun's is yellow ish. So they have very low luminosities, but during flares, they produce extreme energies. How can this possibly happen? Well, several of the ingredients could be one, these what we call flare stars are very young. When stars are very young, they're spinning around very fast. And it's this spinning that we think contributes to actually the magnetic field generation of our own sun. Our sun is much older than some of these flare stars, and it's spinning slower and therefore generating not as many twisted magnetic fields. So these M dwarfs are young, they're spinning really fast. Let me give you an example. There's some of these flare stars are spinning once every half a day to our day to once every 3 days of the Earth. Whereas the sun spins on its axis about once every month, approximately. Okay, so they're spinning really fast, and we think that's an important ingredient. Another ingredient is they have a different structure internally. They are what we call, at least a subset of these, are fully convective. And we think that the magnetic fields in our sun are generated in the outermost region of the interior of the sun called the convection zone, where the hot plasma is boiling. It's turbulent. and also combined with the rotation are the critical ingredients for generating these magnetic fields. The M dwarfs, the entire region, including the core, is boiling. It's entirely convective. So you have the entire volume of the star able to produce these magnetic fields. In addition, when the magnetic fields finally get to the surface, the red dwarfs are much smaller, so there's much smaller surface area for the magnetic fields to kind of spread out, right? So you have much higher chance of interacting if you're a magnetic field that goes to the surface of an M dwarf. You'll find, oh, there's another magnetic field right there. Darn, we're gonna, get all tangled here and produce a flare.
Yeah, so we're talking about these M dwarfs that have these huge flares, and we talked a couple weeks ago with Dr. Zach Berta Thompson about looking for exoplanets, and one of the places that we primarily look for these exoplanets is around M dwarf stars. So I imagine that, smaller flares that we have here on our sun will affect Earth. Could these huge flares be pretty bad news for any little exoplanets going around these M dwarf stars?
Yeah, in fact, this is a matter of current debate of whether the flares of M dwarf stars make affect the habitability of planets around M dwarfs. I think it's still an open question. There are aspects of M dwarf flares that we still need to understand better. In particular, we need to understand if M dwarfs produce coronal mass ejections, like the sun produces coronal mass ejections during large flares. We've never yet directly detected a coronal mass ejection during an M dwarf flare, and that's kind of the frontier here, is trying to figure out a way to detect the mass and magnetic field, okay, which really doesn't produce much light from these M dwarfs. The thing about the habitability around M dwarfs is because they're so small, and when they're not flaring, their luminosity is 10 times lower to 1,000 times lower than the sun. So for a planet to be habitable in the traditional sense, the planet needs to be really close to the star to get enough light to make water liquid on the surface of the planet, if there's water. Now, if the planet's a lot closer to the star, that means that the amount of flare light and the amount of mass from a hypothetical coronal mass ejection is a lot more, because the light spreads out through space, and the mass spreads out through space. We're sitting pretty comfortably here at the distance 150 million kilometers from the sun. But an M dwarf's habitable zone is anywhere from 10 times closer to 20 times closer, even closer than that. Okay, and that means that if you have a planet that's 20 times closer to the sun, the flare energy is 400 times more. You can see it goes up dramatically, the amount of flare radiation that impacts the planet. So we're still trying to understand all these different effects on the planet. There are several obstacles we need to know about the planet itself. How thick of an atmosphere does it have? Does it have a thin atmosphere like Mars, or does it have a thick atmosphere like Earth, or a very thick atmosphere like Venus? What kind of magnetic field does the planet have to protect it from the potential coronal mass ejections? So really, there are some unknown variables that hopefully we'll get a handle on soon, with a technique called exoplanet transit spectroscopy. Right now, we're still kind of figuring out, the impacts of normal flares on red dwarfs, and also what we call these super flares or mega flares, flares that are 100 or 1,000 times larger than the biggest solar flares we've ever seen.
So, I know that exoplanetary science is not, your primary field, but I'm curious, and I guess we have Tara here who is quite interested in that. What would be the possibility that, in fact, the flares, the abundant, very large flares on these M-type stars, could actually help the habitability, like aid the habitability of planets that are further out, right? Because we mentioned that it's much cooler, the surface is much cooler, so you have to be way closer to your star as an exoplanet to get
Right.
the amount of light that you need for liquid water. And so could it be that, I kind of think of these solar flares as hostile, things, that they're dangerous and they would be dangerous. But is there any thought about that they actually could provide the excess heat and light needed to then heat, planets further away from those stars to, temperatures that would sustain liquid water, for example?
So the the interesting thing about M dwarfs is they can produce their impressive flares for a very, very, very long time, for billions of years. Okay, so our sun produced much larger flares in its first billion years being around. Okay, but then it became significantly less active in terms of its flares, and here we are at 4.5 billion years. Okay, and the sun is, a pretty tame star compared to these red dwarfs. But these red dwarfs stay um, uh, producing. They keep producing these big flares for billions of years. And this is another kind of open question. So, given that life takes some time to develop, this very active state will be something that the planet will be subject to for a long, long time. And so we finally now have accrued a lot of statistics on these M dwarf flares from data from the Kepler satellite. We've had very long stares at these flare stars, and now we're combining it with other data sets to get a longer term understanding of, at least on years, decades timescales now. So the billion year time scale, yes, certainly there could be cumulative effects. And I think that, however, ultimately there will be unknowns with the planet, for example, volcanism, the atmospheric properties, the magnetic field, which will affect any cumulative effect of flares. As far as helping life, well, we still don't know how life developed on Earth, what the trigger was for it. Um, uh, but there have been studies suggesting, that high energy radiation, for example, UV light, can cause mutations, which are helpful and harmful. So there could be a kind of a double-edged sword to a more hostile X-ray and ultraviolet environment around these stars.
So in order to study these stars, both our sun and these other stars that are not our sun, that are further out from us, we use telescopes, right? That's kind of the astronomer's view into the universe. And you do a bit of work with ground-based telescopes, including the brand new Daniel K. Inouye, I don't know if I'm saying that right, Inouye telescope in Hawaii. What are some of the features of DKIST? That's what the acronym that solar scientists are so excited about.
Yeah, so there are a number of aspects to this telescope. Uh, one is that it has a brand new suite of instruments. And you can operate almost all of them at the exact same time. So you basically have a Swiss Army knife for looking at the sun. You can look at it in a bunch of different ways, meaning different wavelengths of light, different colors of light. Um, at the exact same time. And each of these instruments is like a super version of what we have currently on our best ground-based telescopes here. In addition, there are a couple brand new techniques entirely that are being used with the DKIST to study the sun. One, though it's an optical telescope, that is, it will measure the light and from the blue all the way through the near infrared. It will also be able to probe the corona. Now, the corona is millions of degrees, and it radiates primarily in X-rays, okay? But there are some signatures in the optical. And only with the DKIS's new capabilities can we now measure certain properties of the corona. It's really awesome now that we have such a huge mirror looking at the sun, because we can start to see some of the what we call the fundamental scales, or the most important scales that drive the physics.
How big is that
sun.
mirror, by the way? Just really quick.
It's 4 meters
In diameter.
in diameter.
Okay.
Right. So what new capabilities do the DKIST have looking at the corona and in the photosphere, chromosphere? Well, it can measure not just the brightness of the light, but another property of light called the polarization of the light. Okay, and this is brand new for this type of observing. And what we can do with that is we can measure more than just the temperature and the density that we've been doing with just the amount of UV to optical light or X-ray light in one part of the X-ray band to another part of the X-ray band. But we can actually start to measure the magnetic fields and the electric fields in the sun. We still, though the sun produces magnetic fields very, very well, and we see the sunspots, we have a very limited understanding of how these magnetic fields are generated and what the strengths of these magnetic fields are throughout the atmosphere. Okay, we know that they're large in the photosphere and we know they're weak in the corona, but we really don't have an idea on their strength throughout the entire atmosphere, going from the photosphere to the chromosphere to the corona. And we're going to be able to figure this out now. So these are some of the capabilities that will become readily available for solar physics in the 2020s here.
So with this huge mirror, I'm guessing we're gaining a lot as far as resolution as well?
Yes, we are gaining a lot in terms of resolution. We are gaining we can see details that we've never seen before in the sun. And the best observations of the sun that have been done have already been resolved by a factor of 4. And typical observations of the sun from the ground are going to be regularly outdone by a factor of 10. So we're really seeing some fine details in the photosphere and the magnetic field in the photosphere as they stick out of the surface, how they interact and bounce around and get stretched. In flares, we're also going to see much more detail. I study the UV, ultraviolet, and the optical radiation in the flare, which tells us how the deepest layers of the solar atmosphere are heated. And when we look currently in the UV or optical, we see little blobs, okay? We see little blobs of bright blue and UV light. And these blobs are not so little, they're about the size of, say, Lake Michigan. But with the DKIST in a 4-meter mirror, we're going to be able to see much finer detail. The thing is, when things are small on the sun, they get smeared out and you don't see detail. In addition, the intensity, the brightness of the blue and optical light gets smeared out. So for the first time, we're going to be able to measure the absolute brightness of these flaring blobs, what we call kernels, in flares.
So we also have this brand new spacecraft out there, Parker Solar Probe, that's been getting some really awesome solar data. Do you guys kind of work together with the spacecraft and the telescope, kind of planning observations or sharing data? Or there seems to be a lot of really cool stuff going on right now.
Yeah. So there are collaborations being developed to coordinate observations with the DKIST and the Parker Solar Probe. The Parker Solar Probe taking measurements, local measurements of the fields, magnetic fields in the outer corona, and the electric fields and the solar wind. And then basically the DKIST will provide very, very, very fine detailed images of the surface, so that we have basically, we're basically taking a thermometer with Parker Solar Probe to the outer corona, and we're taking very detailed pictures of the surface where these magnetic fields originate. And so we can get both, a local picture of what's going on and see what's happening in the surface, so we can connect these very large range of distances from the surface all the way out. So it's going to be a really interesting combination of what we call in situ temperature taking and remote taking spectra.
I imagine that with this, huge primary mirror of DKIST, that it's going to get really hot, because we're looking at the sun, which is hot, and even looking through binoculars at the sun, you can literally burn your eyes. How, from a technological standpoint, do you know anything about how they're controlling the temperature inside of the telescope so it doesn't just melt?
Yeah, very carefully. Actually, it's a major engineering issue, and what they have is a giant airflow system that basically blows cool air across these mirrors, so they don't overheat and you don't get literal fires. We've had first light, it's worked, we're all safe. I've observed the sun from a smaller solar telescope in New Mexico, only 1 meter diameter mirror. There's a very sophisticated system here to basically allow you to stare at the sun and amplify its light. Typically we have a lot of photons, we can put, if it's too bright, we can put a bunch of filters in front to kind of dim the amount of light so that we can actually see the detail. That's one strategy. But really, it's not as big a problem as one might expect due to these airflow systems and cooling systems that we have here. It's a pretty advanced cooling operation they have there, keeping everything, at a decent temperature.
I feel like we should give the obligatory, for all listeners listening to this podcast, do not look directly at the sun. It will lead to eye damage, and we are not responsible for any medical problems you have going forward after you listen to this episode.
So in addition to just your studying stars and flares and things, you also have been doing a bit of developing new media with the purpose of kind of bridging the gap between this really high level complex solar science and the general public and people who don't necessarily study solar physics. So can you tell us a little bit about some of the work that you've done in this area, kind of making this science accessible?
Yeah, so first, my first step is soon I'll be releasing a brand new website with general information about stars. flares, solar flares, M-dwarf flares. And in addition, I'll have some technical sections at different levels, and flare movies for people to download. That's my first step. But my ultimate goal is to basically bridge the gap between these very technical research papers with a lot of jargon, for which even other astronomers not in your subfield sometimes have a hard time following. And then there are articles on the other side of the spectrum here, on New York Times or BBC, which are often extremely very well written, and I monitor them myself to get some of my news in astronomy. But there's this middle ground here where if you have for example, a young student who's eager to learn a little more than what the completely plain English articles in the newspaper say, but someone who has not maybe gone to college yet to get the physics, or has not gone to grad school to learn all the astronomy jargon that we use, right? And so there's this kind of middle ground where I feel that we're lacking in kind of fulfilling, delivering to very eager people who are just want to learn a little bit more, who want to go in a little deeper. And so I have this idea, encouraged actually by my sister, and inspired by my sister to do this, to keep going with this idea as things have gotten really busy with my work here, and which is to create a 1 to 2 page resource for each technical article that's written, that has one actual figure from the paper, and that's written in essentially plain English, by the primary authors. So it kind of creates a intermediate resource for those who don't want to read a 40 to 50 page journal article, and who just but want to actually get some physics and maybe an equation and maybe a professionally published spectrum of a flare or something, who want to see the actual data that led to these inclusions, because often you don't really see in the popular articles, you don't see the proof. Well, why are the authors claiming this? Where is the proof? And we're asked to basically trust. The public is asked to trust the conclusions here, but really to actually show some of the proof to the public, I think would help the appreciation of science in general, in addition to help the student, the more proactive, eager, science-oriented high school students out there, or middle school students who just want to learn a little more.
Is this like an online collection that you're doing, or
it will be an online collection? Yeah.
Okay, so maybe not like a compilation supplementary textbook or something.
No, it'll be my ultimate vision is to basically recruit all fields, starting with astronomy and then bridging into physics, and then going to, say, biology and chemistry. So to bring in essentially all these natural science fields together. In addition, I mean, things like that would definitely help me. For example, the physics and particle physics, and that's full of their own jargon, and they're knee deep and their own pursuits. It's really hard to get an intermediate stance on some of the cutting edge frontiers of physics, and that would really help me. So it's also for other scientists to maybe more quickly get up to speed on some of the what's happening in fields they did not go to grad school in.
I was just thinking that exact same thing. That would be wonderful. Like I do, a lot of geophysics stuff, but occasionally I need some chemistry or I need to know about magnetic fields in a little more detail. And not necessarily I need to spend a year studying this and reading all these papers, but just kind of a quick overview of this is how this particular thing works. That would be incredibly helpful.
Yeah, that's a big part of I would like the reason why I'd like to see this happen is to facilitate interdisciplinary research, so that you can get started on your own more efficiently. If you need to borrow, go to some, for example, for me, if I want to research, learn more about lightning on Earth, it's where do I even begin? Where do I even begin with that? So one of these articles, 1 or 2 page articles, could be a place to start where you get some basic physics, and then you have some references to dig in deeper.
This is a brilliant idea. I would be so pleased if your project really like took hold and just became almost as if like instead of just writing that abstract, which is we often find at the top of these, almost always at the top of these papers, that really kind of briefly summarize the paper, kind of adapt that into like this readable article for someone that isn't in the field. And it just summarizes, here's what we talked about, here's what we learned, but it's accessible. And a couple of times on the show, we've talked about kind of building the public trust in science, right? That's something that humanity's kind of always struggled with, and we see it today. That there are a lot of people that like you said, what's the proof? You say this in your article on CNN or whatever, but what's the proof? Like, how do I know that this is real? And that seems like a brilliant way to help establish that trust and allow people to read this and see, wow, this is like a full experiment with undeniable answers. Like it's right there in front of me. The whole thing is just brilliant. That's an awesome idea.
Well, thanks. Thanks very much. It's very encouraging and kind of something that's, I've created a few examples myself already. I just kind of have to get the ball rolling with more than just me. So I
Sure,
need to get.
right. Have you talked to other researchers yet about this? What has been the response so far?
So the response has been very positive, and mostly I've talked with people who don't do science for a living,
Sure.
and they're very, very eager to get into this.
Yeah.
For me to start, really get the ball rolling on this. And the thing is, it's a lot of work for the primary authors.
Sure.
In addition, you have to remake your figures to um, you know exclude the jargon and rename your axes and a lot of these things, and
Right.
whether how to go about monitoring this. There are some logistics, but all these are just lame excuses I'm coming up with now. Reason I haven't pursued this in more earnest, but I have developed several examples myself to send out to authors
Are those
as like,
available
here's what
anywhere
we're looking for.
to look at as like
Yep,
demos?
yep.
Are those just like on your website?
They'll be on my upcoming new
The new
website
website. Okay.
that I'm working on. Yeah,
Great.
they will be. Uh-huh.
And I assume that will just be like linked to on your CU Boulder main
Yeah,
page.
it will be. Yep.
Okay,
It'll be
cool.
the same address as my old one,
Oh, great.
afkowalski.bitbucket.io.
Okay.
It would just be complete redesign with a lot more content and including this stuff here.
Awesome. Well, Adam, in our last couple of minutes here, we always like to ask our guests, was young Adam, I imagine you like standing in your kitchen talking to your parents and they ask, Adam, what do you want to be when you grow up? Was your answer a solar physicist from the get-go, or did that kind of develop, as you kind of went through school? How did you get to where you are today?
Yeah, I did not see myself going into solar physics. Um, Actually, I was interested in astronomy in general since I was a kid. My parents got me a telescope, and we'd go up to a beach resort during the summers, and the skies were just amazing there. You could see to sixth magnitude, see the Milky Way. It was just amazing, and so that kept my interest going. This just backyard astronomy reading Sky and Telescope, watching Cosmos, the Cosmos series by Carl Sagan, reading all of Carl Sagan's books, reading Kip Thorne's books, all these really excellent books on various aspects of astronomy. And then I learned that you had to be very good at physics to actually be a professional astronomer. And then I majored in physics, and in order, to eventually go to grad school in astronomy, it was pretty difficult. And during my college years, it was, I kind of, what am I actually interested in and things like that. And then my senior year, I got involved in a research project with Professor Dietrich Müller at the University of Chicago. And I just was really, really into the whole research thing, particular how he ran his group, the nature of the scientific exploration that he encouraged. And I realized I wanted to apply to grad school in astronomy. And I went to the University of Washington, still not knowing what parts of astrophysics interest me. I did my research project in my undergrad on cosmic rays, particle detectors. So I was really interested in like particle physics aspects of astronomy. And then I started doing a project on M-dwarf flares in grad school with Professor Suzanne Hawley there, and just kind of became extremely interested in the fact that these M-dwarf flares produce this blue and ultraviolet light with enormous luminosity and energy, and yet our computer models had essentially failed to produce anything like it. And so I just really got involved in this in stellar flares, M-dwarf flares, towards the end of my PhD. I started going to solar physics conferences because I knew that we really needed to observe and understand solar flares better in order to understand M-dwarf flares better, because we can see all this detail in the solar flares. And so that's how I eventually got started in solar physics, kind of late, came from the stellar side, sometimes what we call the dark side.
And you've been riding that wave ever since.
I've been riding that wave ever since. Yes.
Man.
Yes.
So how long have you been from the moment you started that project on M dwarfs that really like kind of set you in the direction? How long have you been doing solar physics?
I've been doing solar physics. After grad school, I did a postdoc at NASA Goddard in the heliophysics science division there, where I worked on the computer models with Dr. Joel Allred. And we eventually got these computer models to reproduce the blue and near ultraviolet light that we observed in M-dwarf flares. And then we started extending our modeling approach to solar flares, making predictions for the DKIST. So that's kind of how it all fits together. We have all these new predictions for the DKIST, what it will see in these bright kernels in the photosphere or chromosphere of the sun. So I guess it'd be probably 9 years now from my first time observing the sun at the Dunn Solar Telescope. 2000. Oh wow. 2010. So 10 years.
Congratulations on one
Thanks.
decade of doing solar physics. That's awesome.
Thank you.
So to kind of wrap up our time here, any advice for a budding solar physicist, someone who's really inspired by this, someone who thinks this is super cool? What would you tell them to? Where's a good place to start?
So we have lots of data. We have lots and lots and lots of data that needs to be understood from last cycle of solar flares. There are a lot of flares that need to be analyzed, understood, and we're looking for young, eager scientists to take these data sets and just stare at them and then do some analysis and to run some computer models. So all you need to do is email someone at the National Solar Observatory who does solar physics, and we'll get you started on a research project. I would say that just look on the National Solar Observatory's webpage. There are a list of names and contacts. You can contact me with your general interests. I can forward you to whoever you might be interested in working with. So I'd be more than happy to do that. In addition, solar physics is really great because almost all the data of the sun is nearly immediately public. So you can download the data, all types of data from the sun, just from the internet. You don't need a password. You don't need a credential. You can start looking at solar data right away and doing your own analysis, making your own fun movies. And I can get you started with several tools for that. So just, I guess, contact me and we can get you going with observing the sun.
You know, that's something that we talked about, I think, with Fran Bagenal. Is that right? That there is just, you know, this huge wealth of data that no one has ever looked at before, and it's right there, and it's free, and it's accessible. But there's just so much of it that it's, you know, you can be the first person to lay your eyes on it. And
right.
Yeah.
Right. Yeah. So, you know, there are so many other aspects of solar physics in addition to studying its flares. But I think the same phrase could be applied to all aspects of the sun's very interesting day-to-day life. Is a phrase that my PhD advisor said is so many flares, so little time.
Awesome. Well, Adam, thank you so much for being with us today on the podcast. It has been a pleasure to speak with you. And I think that a lot of people are going to be really excited to start looking into some solar physics.
Oh, great. Yeah. Thanks a lot for having me.